Fellow soil scientists, I'm very pleased to share with you my views for the viewpoint letter of September 1, 2018. It addresses the theme of drought and ancient civilization. The demise of some historic and once thriving civilizations has been attributed partly to climate change and to the ensuing drought. The demise of Akkad, the ancient Iraq circa 2150 BC, is attributed to clouds which refused to rain, popularly called the curse of Akkad. Drought has been a recurring challenge in the Middle East ever since. The fall of the Indus civilization is also linked to the climate change and the prevalence of meteorological hydrological droughts. The mean annual rainfall in the Indus Valley ranged from 800 to 1000 millimeter from circa 6000 to 4000 years before present, but declined to merely 200 to 400 millimeter from 4000 to 3500 years before present. A sharp decline in rainfall over 300 years may have also led to the collapse of ancient Greece about 3200 years ago. A similar problem led to the collapse of the Mayan civilization of Central America, the present-day Mexico. The mean annual rainfall decreased by 40 to 70% during the 800 to 1000 CE compared to the present-day rainfall. During the same period, the decline of Tang dynasty in China is also attributed to weaker Asian monsoons during the 8th and 9th century AD. The ancient Pueblones, dominant across the Colorado Plateau, collapsed due to climate change around circa 12th to 13th century. The famous city of Angkor Wat collapsed in 15th century because of extreme environmental conditions. The severity of meteorological hydrological drought is also exacerbated by suboptimal soil conditions. Soil-related drought and insufficient supply of green water in soil at critical stages of crop or plant growth is intricately interlinked with attributes of soil soil and to properties and processes which determine the plant available water capacity of the root zone. In addition to an effective rooting depth, other determinants of plant available water capacity include soil texture, clay minerals, and soil organic carbon concentration. The latter especially plays an important role in enhancing plant available water capacity of light textured soils containing relatively low clay and fine silt fractions. An interaction between soil organic carbon and clay minerals can alleviate the adverse impacts of drought. Management of soil organic carbon for improving soil hydrological properties such as water transmission retention can reduce the severity and duration of pedological and agronomic drought. In addition to the properties of soil and landscape, the incidence of pedological drought may also be aggravated by the projected climate change. Increase in the incidence of forest fires associated with sizzling summer and widespread heat waves both in Europe and the western United States in 2018 are stark reminders of the adverse effects of global warming. Soil degradation, aggravated by the current and projected climate change, exacerbates the impact of anthropogenic drought. The soil moisture regime, especially the plant available water capacity, interacts with the atmosphere through evaporation precipitation cycle. Drying of the soil, therefore, aggravated by global warming, accentuates drought and its ramification in terms of the loss of net primary productivity and the attendant decline in soil organic carbon stock. Therefore, the strategy must be to adopt management practices which create climate resilient soil and the associated agroecosystem. For the sake of humanity, nature, and the planet, sustainable soil management is essential to alleviate incidences of drought because enhancing soils anywhere enhances life